Now we are going to do problem 9 from section 19 homework. We're given a certain graph that are giving us the limits of integration in this problem, and we need to figure out what those limits of integration are. The first thing we're going to do is try to figure out what the 2 points are here and here. That'll give us a little bit more information about this picture here. And we figure out what these 2 points are by setting x squared equal to 2 minus x squared. And then we'll get that 2x squared equals 2. Dividing by 2, we get x squared equals 1. And then x equals plus or minus 1. When x equals plus or minus 1, y is equal to 1. So we get 2 points, 1, 1, and this other point, minus 1, 1. To set up our limits of integration, we have dx on the outside. So we want dx going between two numbers, and it's going between minus 1 and 1. So we're going to put a minus 1 here. Let me go ahead and do that. And we put a 1 here. So x is going from minus 1 to 1. For each fixed x between minus 1 and 1, inside this region here, we want to draw a vertical line. And we want y to go from the bottom here to the top. So the bottom curve to the top curve. The bottom curve is this parabola y equals x squared. So on the bottom we have the y equals x squared. And on the top is the y equals 2 minus x squared. So we want to go from x squared to 2 minus x squared. So that's the limits of integration here. We're going to put an x squared and a 2 minus x squared. And so that completes the problem. We've set up the limits of integration. From x is going from minus 1 to 1, and for each fixed x between minus 1 and 1, y goes from x squared to 2 minus x squared. For the next problem, problem 11, we're going to use that the volume of a sphere of radius r is 4/3 pi r cubed. And we want to evaluate certain integrals using that formula. So these are the integrals we're given. Let's look at a first. And in all these integrals, we're going to have z is equal to the square root of r squared minus x squared minus y squared, giving us the height. So that's the top of the solid described by this double integral, and we can square both sides and add the x squared plus y squared to both sides to see that this is just a sphere of radius r centered at the origin. So that's what we'll have in all the problems we're going to do in number 11. Notice we also have here an upper limit on the integral for dy. dy is what's going from, or y is going from 0 from square root of r squared minus x squared. So y is equal to r squared minus x squared is the top range on y here. And so y is equal to square root of r squared minus x squared. And we get x squared plus y squared equals r squared here. So these limits of integration for y are telling us that y is going from 0 to a circle of radius r centered at the origin. Here y is positive, going to the positive part of that circle for y. So what does the picture look like? We have x going between 0 and r. For each fixed x between 0 and r, we want y to go from 0 to that circle. And then we want the top part of our solid to be this sphere. The picture looks like this. x is going from 0 to r, that's the x-axis. For each fixed x, y goes from 0 to that circle in the xy plane, x squared plus y squared equals r. So x going from 0 to r, y going from 0 to the circle. And then the top part that we're getting for our solid is this sphere of radius r. So to evaluate this double integral, we just want to know the volume of this solid here. That is the value of this double integral, after all. And the volume of that solid will be 1/8 of the volume of a sphere of radius r, because this is just the part of the solid in the first octant. So we get 1/8 times 4 pi r cubed over 3 for the value of this double integral, 1/8 of the sphere. And that simplifies to just pi r cubed over 6. So the answer for part A is pi r cubed over 6. Let's look at B. So again, we have the top will be of our solid would be the sphere. Z equals square root of r squared minus x squared minus y squared, which again is just x squared plus y squared plus z squared equals r squared. And y is this solid is going between minus r and r, so we're going to go between minus r and r on the y-axis. And for each fixed y in this range from minus r to r, we want x to go from 0 to the circle, where x squared plus y squared equals r squared. So the picture looks like this. We have y going from minus r all the way to r. So the origin is right here in this picture. We want y going from minus r to r. And for each fixed y in that range, we want x to go from 0 to this circle. Okay. So this circle in the xy plane. Okay. So for each fixed y between minus r and r, x again goes from the 0 on the y-axis all the way to the circle. And then the top is again the sphere that we've been looking at before, and we have this picture, which is a quarter of a sphere. And so the volume of this solid is going to be 1/4 the volume of a sphere of radius r, and so this will just be pi r cubed over 3. So the answer to B is pi r cubed over 3. For part C, we have x going between 0 and r. So imagine x going between 0 and r. And for each fixed x, we want y to go from the back of a circle to the front of the circle. This is going to be the same picture I had last time. X is going from 0 to r. For each fixed x between 0 and r, we want y to go from the back of the circle to the front of the circle. So it's going from here to here. So in this part of the circle, y is equal to minus the square root of r squared minus x squared, and this part is equal to plus the square root of r squared minus x squared. So it's going from back here to here. So now we want to take our solid to be that semicircle along with this part of the sphere above it. Again, we don't need to think much here. It's the same answer we had last time. It's 1/4 of a circle, and so it's going to be the same answer as the previous part. It's going to be pi r cubed over 3. For the last part, we have y going from minus r to r, like we did in part B, and x is going from minus the square root of r squared minus y squared to plus the square root of r squared minus y squared. So from the back of the circle, from the point of view of x, to the front of the circle. This is an optical illusion. This looks like the back to me. That could look like the front to you of this picture, of this hemisphere. And y, to me, looks like it's going from minus r to r this way. The origin is right here. So we're going from minus r to r for y. for each fixed y between minus r and r, we want to take an x, and it's going from what looks like the back to me here, from minus the square root of r squared minus y squared to plus the square root of r squared minus y squared. And again, that might look differently to you, but that's how I'm seeing this hemisphere. In any case, it's half a sphere, so we want the volume of 1/2 of a sphere